Good. Hello, everyone. And let me start with thanking Gediminas for putting together this beautiful workshop here and for inviting me and giving me the chance to present not this, actually. So sorry, Chairman, I have to correct you. I took the freedom to change slides, to change the talk because of we are very excited, actually, about new results we have in our Fermi-Hubbard system, where we now observe magnetic polarons directly, in a sense that we really, I mean, you can imagine we take a picture of those polarons, including the distortion of the background, and I want to share that with you. If you have questions regarding this story, I'm happy to talk about that in the breaks. Okay, so it's about magnetic polarons in Fermi-Hubbard systems, and well, I have to show these motivational slides. Well, the Fermi-Hubbard model, besides being a very interesting toy model to study all kind of phenomena, well, ab initio, if you like, in strongly correlated many-body physics, also has this nice connection to solid-state physics, where it's believed to be well, an electronic toy model for the high TC cuprate materials. And this is actually a fairly recent proposed phase diagram for the cuprates. And the interesting region here that basically it poses many open questions is at these low temperatures at finite doping, and that shows you already actually that what is probably most interesting in the model is somehow to study the interplay between charges, that's the story of doping, and magnetic correlations that arise there, yeah? So, and that is basically where we tailored our experiment for. So, well, this slide can be quite quick because of Fabrice introduced it already. So how do we get actually Hubbard models in optical lattices? So first of all, well, maybe, what is an optical lattice? Well, it's made by interference of 1, 2, or 3 laser beams going from pancakes, tubes, to a 3D crystal in space. And now if we throw in mobile quantum particles, in our case lithium atoms, then they can hop around from side to side. And by the way, for the fermions, we are working with 2 spins, otherwise would be quite boring. So these are the red and the blue guys, and well, they can hop with amplitude t, they can interact with different spins on the same side with amplitude u, and actually there's an emerging magnetic energy scale where you basically have spin exchange without charge exchange that goes in second order as 4t squared over u. So these are, so to say, the 3 important scales in this problem. Okay, so our system is a quantum gas microscope where we can image each individual atom side by side, and we actually have a pretty special optical lattice setup that is basically a 2-dimensional super lattice that we make basically by spatially Fourier transforming this pattern with the lens. Actually, in the talk, we make use only of a super lattice in one direction, and in the other direction, it's a normal lattice. I just want to flash that you understand quickly the setup. It's a pretty involved setup for the imaging, and just to show you that this is somewhere really existing in the experiment. That's a picture, basically, of the complicated optical setup. But I'm not going into more technical details now. So I want to show you actually what is actually the specialty that I mentioned already. We can really image not only spins, we can image spins and charges, that means density, at the same image. This is the important thing. So what you see here is basically a preparation of 5 1D chains in this case, and color-coded is basically the fluorescence that we observe atom by atom, so one atom, another atom. In this cell there is no atom. But you observe, for example, also sites here where we see clearly higher fluorescence, and that comes actually from doublons, or 2 atoms on a single side. So, but now how can we have spin imaging on top? Well, what we do is actually we use the super lattice to split vertically here a single well in 2 wells, so here in 2 wells, while having actually a magnetic field gradient on and making use now of the opposite magnetic moment. We can split the spin-ups to the lower cell here. You know, you see here basically we have 1 cell here, we have 2 cells, well, it's hard to see, 2 cells here, see it better where the atoms are, and then we know basically before imaging this one here is a spin down, spin up, spin down, spin up, and that here is actually a doublon on a single side. So we have full information about basically the 4 local basis state in the single band Hubbard model. And that means basically we have full access to spin-spin, and spin density correlation. So we can study, if you like, what happens actually around a single doublon or hole in terms of the magnetism. And that's exactly what I'm going to talk about. So let's start simple and start in the 1D case. So what do we expect in the 1D case? So here's again the Hubbard model appearing something like 10 times on my slides. So let's see what happens. Let's focus on the charge sector. Let's say we have, let's say, a doublon or a hole in the system. What does the hole want to do to minimize its energy? Well, it wants to minimize kinetic energy. That means it wants to delocalize as much as possible. That's what I indicate by this basically continuous gray here everywhere. Now, if we look, treat these sectors as independent, what does the spin sector wants to do? Well, the Hubbard model actually in the unity filling case maps actually to a Heisenberg model. So an antiferromagnetic Heisenberg model, you see you have a positive sign here for the J. That means the spin sector actually wants to align antiferromagnetically through the chain. So now the question is, okay, let's ask the question, if I have now both together, what is actually the spin alignment around holes? And I give you two possibilities. So either we have around that hole antiferromagnetic spin alignment, or we have around that hole ferromagnetic spin alignment. By the way, if I would have here a spin, it's clearly this case. You see it's down, up, down, yes? So, but now, if this is a mobile hole, that means basically in the ground side I have to add a superposition of this hole being at all positions. And you see in the second case, if I move that hole by one side, it costs an energy J. While in the first case, you can just move that hole around, so it doesn't cost energy. So the lower energy state is clearly this case, and now again why I mentioned that is basically a case where, compared to the fully filled case, those two spins changed. And they are now anti-parallel, while otherwise they are parallel. So let's see if we can see this in the experiment. So we calculate exactly a correlator. Well, that's basically a standard the standard magnetic correlations that we see in the experiment. So you see basically at the distance of 1, the spins are anti-aligned, they become aligned, they are anti-aligned, aligned, and so on and so forth. So the standard tic-tac. And now let's look at what happens if we single out events where we have a hole. So we clearly see that the sign of the magnetic correlations around that hole spectacularly change, actually. So now, if you think of what happens by this sign change, if we have a fluctuating hole number in the system, then that, of course, completely suppresses the two-point correlator, because now if I once, in one shot, so to say, have that hole, in the other shot don't have that hole, I average a positive and a negative number, so it should go away, basically. Yeah? That's how, basically, doping seemingly suppresses magnetic correlations. I want to show you actually in which sense this is actually not true in 1D, and that is just given by the inability of the two-point correlator, the standard one, if you wish G2 in spins, to basically separate between the charge and the spin sectors. So this is a typical spin-spin correlator. Those disks and dots, by the way, I didn't mention, mean the sides are filled or the sides are empty, so this obviously means filled. Before there were empty ones, which means side is empty. So now let's see again, the little cartoon, I have a fully filled chain here, and now assume I have a hole at this position. I explained to you already that that means this spin now is up instead of down, and then it goes on, the standard nail order. I have another hole, and again, I'm again in order. And now, of course, if I average the two, that was what I said, this goes to 0. But now I can reveal, actually, the still present order in the spins by going into squeezed space. And what is squeezed space? Well, the idea is basically I just squeeze out all those holes. You know, I just press this chain together, and the holes are gone. And what I recover is a perfectly Heisenberg-ordered spin chain again. But that, again, amounts to a very non-local measurement, because, you know, I want to measure correlations between this spin, and I have to know each and every hole in between. Yeah? So it's not only this two-point correlator, I have to know everything in between these sides. Okay, we can do that. So what you see here basically is now three different traces for 3 different dopings. So the green one is basically around unity filling, and then we increase the doping from over red to blue. So you see the green one shows the standard tic-tac, the red one shows this already much weaker, and the blue one basically doesn't show any alternating sign in the correlations anymore. So now let me squeeze out the holes. If we squeeze out the holes, it's all the same, basically. So you see here basically that in reality you can separate the spin sector from the hole sector. You just have to take the right observable, if you like, and then you see basically that the spins, they don't actually care for the holes. So in this sense, this is actually a very local manifestation of spin charge separation in the model, not in the dynamical sense, but just in the sense that we see this directly at multi-point correlations on equilibrium states. Okay, that was for 1D, but you see now actually another thing that happens is, if I spill holes into the system, then you can also see this as the average distance between two anti-correlated spins increases with the hole number, yes? So we took a lot of statistics actually, because additionally to this increasing distance, I explained you the amplitude goes down quite strongly. Nevertheless, if you take enough statistics, you can still see that this dilution of the magnetic correlations due to the addition of holes actually leads to a stretching of the antiferromagnetic correlation of the wave vector and leads to incommensurate magnetism. So what you see here, the blue curve, is basically the tic-tac in a strange log-log plot to see basically the small correlations that show basically commensurate correlations. So it's down, up, down, up. And now if we go to 20% doping, we see basically the second point here changes effectively sign. And if we follow that, that effectively leads to a stretching of the magnetic wave vector and doesn't match the lattice anymore. So that's incommensurate correlations. That's actually predicted by Leitinger theory. So basically a scaling of the wave vector of the correlations with the number of holes. And well, in this color scale, I think you see it, we can make a Fourier transform of all those results versus density, and we really nicely see this linear wing going out here. So we can really directly see this incommensurate correlations. So this is all a 1D story. And I promised you something about polarons. There are no polarons, obviously, in 1D, because 1D, I tried hard to convince you that the spins do not care for the holes, but the polarons is exactly the story where the spins care for the holes. So yeah, so what happens in 2D? Let me start with a similar picture as I've shown you in 1D before. So we have a doublon here in the center, and a perfectly, well, I always draw a Néel order, just to remind you, this is of course SU2 symmetric Heisenberg model, but it's hard to draw. So that's the perfect Néel order cartooned around this hole. And now if this hole is mobile, again, we have to add a superposition of several terms where this hole is doublon. In this case, it's doublon. Before it was a hole, now we look at doublons. I can explain why later. Now we add terms where this doublon is at different positions, and we see when we say we sit this doublon, we move it to here. That basically means we move the spin to the right, and now we have here 3 bonds that are wrong. So this costs 3J energy. We move it one further. We have 5 bonds that are wrong. That costs 5J energy. And this cartoon picture obviously assumes that the spin background doesn't react. So super exchange does nothing, and I just do take the T part into account. Yeah, so this is a very simplified picture of that. But you will see that that is actually, well, to the precision we have at the moment, matching what we see. And that basically means also in this picture, because of course you don't have infinite energy available, the distortion of the magnetic background around such a doublon that we find should be limited in space. And that's exactly what you expect for a polaron. You know, you have a background, and this background is locally deformed due to the defect that you have. So that is basically based on an idea that Fabian Krust and Eugene Demla developed, and that is what they call a string picture between a spinon and a holon. So that's basically the theory background behind that, and we have strong correlation with them. But what I like to show you is actually that you get a theory-independent comparison of the case of having a hole, or well, doublon. Oh, sorry, excuse me for hole and doublons, it's doublons. For a doublon that is fixed in space, to the case where you have a doublon that is allowed to move around. Yes, so this here is basically a doublon that we fix by a dimple beam basically, and this is the density, just the density pattern for doublons that are allowed to move. So you see the doublons are allowed to move in something, a region like this. So remind you, this is a region of something like 3 to 5 times 8 or something. That's important to see later, that the polaron extent actually is smaller than that one, yeah? Because otherwise you say it's just a density effect. Okay, so this is what we see. So I have to explain these maps. Let me look at still some time. So what I plot here is basically, I measure 3-point correlators in the sense, I look at the stack of images that we have, find out where's the polaron, center this polaron on these maps, and then look around what is the magnetic bond strength around that polaron. So that's plotted here in this slightly unorthodox plots. So you have the polaron, and in this case we look at the diagonal magnetic correlations around that polaron. And in this case, where we have a pinned polaron, they are all positive, they are all red. And that is actually what you expect for nil order. Maybe if I go back. So you see the diagonal ones here, they are always aligned. Yes? If we do the same thing, but now for nearest neighbor correlators, they are all negative. So for this, I don't have to go back as nil order. They are all negative. Yes. So now let's set this polaron, this doublon free, and let it move. And that's what you see. What happens? So you see the diagonal correlator even switches sign. It goes negative instead of positive. And the nearest neighbor correlator shows basically decreasing correlations around the position of the doublon. So now we can basically, make this a little bit more quantitative and radially basically average those maps to get an idea of the size of this object. Yes. So that's what's shown here. So you see here basically something that we call bond distance. What is bond distance? That's basically the center of the link. So in the end, it's just a way of quantifying the distance in some way of those correlators. And in this case, it's a diagonal one, and you see directly compared pinned versus mobile. So you see a little bit of change in the pinned one too, and that you can understand actually if we pin a doublon at one side, we block out 4 bonds out of this Heisenberg model, so you expect something to change basically. But you see a dramatic difference at short distances between the pinned and the mobile Kais, and actually they go together at long distances. And you see actually here the sign change. Actually the sign change, it's easily understandable because what the moving doublon does effectively, it replaces a next neighbor correlator with a diagonal correlator, and that changes the sign basically then. And also in the nearest neighbor case, you see qualitatively the same effect. The two cases, they nicely match at large distances. At short distances, they really strongly diverge from each other, and we see basically that the pinned doublon basically shows little response actually in the other direction, because that's actually a reason. That's actually an effect because we have a boundary there now, so the correlations get a little bit stronger. While the mobile one does the opposite; it gets weaker. So in this case, up is weaker. That's a negative axis. Okay, with this, I think I already want to summarize, and I thank you for your attention. And this is the lithium quantum gas microscopy team at MPQ, with strong support here by Eugene and especially Fabian. And summary, I showed you how we can study actually hidden magnetism, spin charge separation in one dimension in a quite unorthodox way. How we can see incommensurate magnetism, and now this very recent results about, extending this one to 2D, where we see these magnetic polarons emerge. Okay.